we're going to look at a common cathode amplifier in a little bit more detail and a little bit more of a real-world example of it. So here we have the common cathode circuit as we've looked at it. We have a resistor going from the anode to the positive voltage. That's there to convert a changing current through the tube into a changing voltage for our next section. We have a capacitor going from the anode to the output so we can get rid of DC. We have cathode connected to ground. Our input goes to our control grid, our output comes from our anode through that capacitor. So again, that's the circuit as we've been looking at it. Over here we see our input, a nice clean sine wave, and our output is opposite in polarity, which is something we know is going to happen in a common cathode circuit. The top part of it looks fine, but the bottom part is all flattened off. And that's what we call clipping, which sounds like distortion. It is distortion. That's not something we want to see in an amplifier. Whenever we look at a circuit and analyze what's going on, we have a process that we'll use. I'm going to start introducing this now. We'll get a lot more into it in later semesters. The first step is always to list the characteristics of the components. Now we have a resistor and capacitor here that we're not going to list. So hopefully you know them at this point. But since it's new, we will talk about the triode. So in a triode we have an anode, which needs to be more positive, and a cathode, which needs to be more negative. Electrons flow from the cathode up to the anode. A positive voltage on the grid increases current flow, and a negative voltage decreases current flow. When we get to our maximum current, it's called saturation. When we get to our minimum current, it's called cutoff. Again, those should be reviewed, but just it's good to list them as you're looking at a circuit. Just to make sure you understand everything about the circuit before you dig into it. The next step is to list the characteristics of the circuit type, or the sub-circuit. In this case, we have a common cathode amplifier circuit. So the things we know about it. The input's on the grid, the output's on the anode. That's really what defines it as a common cathode. We have a resistor going from the anode to the positive voltage, and that converts a changing current through the tube into a changing voltage for our next amplifier portion of the circuit. The output is the opposite polarity as the input. And in a good amplifier, we should reach saturation and cutoff at the same level of input. So what that means is that I should be able to go as positive from 0 before I reach saturation as I can go negative from 0 before I hit cutoff. Most audio waveforms are symmetrical, or at least average out to being symmetrical, so we need to have that room to go both positive and negative in the same amount. So our next step is to identify the problem with our output. So our output is clipping at saturation before it's clipping at cutoff. So what hopefully is a little bit obvious is that it is clipping at one of those 2 points before it's clipping at the other. What may not be quite so obvious is that it's clipping at saturation and not at cutoff. This is the more negative part of the waveform. That seems like maybe that should be cut off. So let's look at what happens. As we make the input voltage more positive, we are increasing current flow. That means we are moving toward saturation. As we make it more negative, we are decreasing current flow, or moving more toward cutoff. Because the output is opposite polarity from the input on this common cathode circuit, this positive change in voltage on the control grid creates a negative change in voltage on our output. So this is moving more toward saturation, this is moving more toward saturation. So this clipping point is actually saturation. So we have this resistor there to convert the changing current through the tube into a changing voltage. And that's why that resistor needs to be there. One effect of it that we don't necessarily want is that it changes the polarity of our output. As we make our input voltage more positive, we increase current flow through the tube. That means increased current flow through R1. Increased current through R1, Ohm's law tells us, means an increased voltage drop. At the top of this resistor is a fixed positive voltage. If its voltage drop increases, that means this point in the circuit has to become more negative. So a positive voltage on the control grid increases current flow, increases voltage drop, which makes this point in the circuit more negative in voltage. So that's why we get this inverted polarity. So again, this is saturation, and we're clipping at saturation, but we're not clipping at cutoff. And ideally, even if we were clipping at saturation, we'd be clipping about the same at cutoff. So that's the problem that we need to fix. Ideally in a tube, when there's 0 volts on the grid, the amount of current flowing through the tube is halfway between saturation and cutoff. We looked at that a little earlier. That way we have as much room to make the control grid more positive toward saturation as we do to make it more negative toward cutoff. Again, audio waveforms are symmetrical, so it's important that we be able to do that. What's happening, because we're hitting saturation too soon, is that our control grid is too positive compared to the cathode. So there's too much current flowing when there's no voltage on the control grid. So we don't have as much room to make it more positive as we do to make it more negative. So one option would be to make the control grid more negative. Unfortunately, we don't have any negative voltages in the circuit right now, so that would be difficult to do. However, what's really important is the relationship of the control grid to the cathode. The electrons leave the cathode. All they know is the voltage they came from and the voltage they're heading toward. So we could make the control grid more negative, but we could also make the cathode more positive. And that would do exactly the same thing as far as the electrons are concerned as if we made the control grid more negative. So how are we going to do that? We have current flow going from the cathode down to ground. We have current flow, we want to create a voltage, we use a resistor. So in that current path we now have a resistor. Current's flowing through this resistor, creating a voltage drop. The bottom of the resistor is at 0 volts. So the top of the resistor is at whatever voltage this resistor is dropping. So let's say it's dropping 1 volt. Then the cathode is now at 1 volt. So when the control grid is at 0 volts, it is negative in comparison to the 1 volt of the cathode. So we've made our control grid more negative comparatively to the cathode, and that has fixed the problem. So if you look over here, you'll notice now that we have a little bit of rounding off or distortion on the saturation side, but we also have exactly the same on the cutoff side. And that's what we want. We want them to hit saturation and cut off at about the same place. So that's good. However, you might notice that on our earlier waveform, our positive voltage went almost to the top. But now it's really reduced from that. So we now have less output than we had before, which isn't particularly good. So why is that happening? As we make the control grid more positive and increase current flow through the tube, we're also increasing current flow through R2. That increased current flow through R2 creates an increased voltage drop, making the cathode voltage higher or more positive. What controls current flow through the tube is the relationship of the control grid to the cathode. We make the control grid more positive compared to the cathode, and we increase current flow. Well, now at exactly the same time we're doing that, the cathode is becoming more positive. So it's moving up in voltage along with the control grid. We get less of a difference in the voltage between the two, so we don't get the increase in current that we had before. What this all means is that we have less amplification now with this resistor on the cathode than we did without it. We fixed our distortion problem of hitting saturation before cutoff. We have less amplification. How are we going to fix that? Coming from ground up to the cathode, we have AC riding on DC. We know this DC because current can only flow in one direction through the vacuum tube. But our varying voltage on our control grid creates a varying current through the tube. That variation, that change, is seen as AC to the capacitor. So that will flow through the capacitor. And as long as we make the capacitor large enough in value, there'll be no voltage drop for that. The only voltage drop will be the steady current that's flowing through our tube. So not changing, but basically the current flow that's created by this 0 volt on the input. So our halfway between saturation and cutoff. That's going to flow through R2. Any changes we make will flow through C2. If C2 is made large enough again, there'll be no voltage drop for it. So like the pig from Unit 4, we'll see that there's no change in voltage here, even though there's changing current going through C2. So whatever current is flowing through R2 will hold the cathode at that stable voltage. In most cases in a triode circuit like this, that's 1 or 1.5 volts, maybe 2. To make it more positive than our control grid when it's sitting at 0 volts. One of the important parts is that path for the AC is close to a 0 reactance path. So all the audio, the changing current is going to flow through C2, the stable current is going to flow through R2. That means our cathode is now going to stay at a stable voltage. So now we've fixed the problem in our circuit. And here we have a common cathode circuit showing all of the components you'll normally encounter in a common cathode circuit. It also has a really slow animation that will let you look at how the control grid changes along with current flow through the tube, output voltage, and cathode voltage. So you can see all those in real time. So let's look at our components. Up here we have R1 connecting the anode to the positive voltage. That makes the anode positive so that the electrons can be attracted to it. But the reason there's a resistor there instead of just connecting the anode to the positive voltage is so that we can convert that changing current through the tube into a change in voltage to connect to another control grid of another tube. Now if this were an amplifier connected right at the end of a circuit, where the speaker would be the next component that you would see, most likely instead of that resistor there would be a transformer. The transformer can take that changing current, convert it into a changing magnetic field, and then convert that into changing current on the other side. So it doesn't need a changing voltage. So you won't always see that resistor, but you'll often see it. And certainly if it's going to another tube, you will need that resistor to be there. Then we have R2 down here connecting the cathode to ground. Again, that is there. That's just the component we just put there. So it is there to move the cathode above ground and center current when there's 0 volts on the control grid, halfway between saturation and cutoff. That gives us as much room to make the control grid more positive and increase current flow toward saturation as we can make it more negative and make current flow move more toward cutoff. Then we have C1 here between the anode and the output. Through the tube we have AC riding on DC. For the next stage of our circuit, we just want AC in most cases. If we were to put AC riding in DC into the control grid of another tube, we'd send it way into saturation right away. So we need to get rid of that DC. We do that with a capacitor. We have C2. Again, C2 is there because with R2 and not C2, we have a reduction in amplification. When we add C2, it becomes a low reactance path for the change in current, so that there's no change in voltage across the cathode as we change the voltage of the control grid. So there you have a typical common cathode circuit.